So a dual stage controller. Now let us first consider, I don't consider a single stage controller. Maybe it's still interesting for you to investigate if it can be done with a single stage controller. You will find a very low loop gain, and that means that the transfer will very much depend on temperature, on device parameters and tolerances. So let's say we are going for a thing that can do it more accurate, in which feedback really has a meaning, and immediately we are going to a dual stage solution. So dual stage amplifier. But if we take our CS input stage and our push-pull CS type output stage, then we have a non-inverting controller. Having a non-inverting controller means that we cannot make negative feedback. We have positive feedback, and that unfortunately would not result in a desired behavior. We create something like a flip-flop or an oscillator, but definitely not an amplifier. So what we could do is replace one CS stage with a non-inverting stage. For example, we could do it at the input. We could say, replace the input stage with a CD stage, a common drain, a source follower, or use a complementary CD stage at the output. Without doing a lot of calculations, we can already predict what will be the behavior, what will be a disadvantage of doing so. For example, by taking a source follower, a common drain stage, at the input, we know that from the transmission parameters A, B, C, D, A is unity. That is what is happening if we make a local feedback voltage amplifier with feedback, with unity gain feedback, and that is basically the CD stage. So we would have A equals unity, which means that voltage noise of the second stage is just added to that of the first stage. And we are already, let's say, struggling a little bit with the noise. I mean, we have the specification, we can make it better, definitely, that's true. But to add more voltage noise from the second stage would not be a good idea. Now, you could also think of making the output stage a complementary CD stage. A very popular one, by the way. But that means that driving the output stage, the drive voltage for the output stage needs to be equally large as the total load voltage across the 100 ohm, which means that the stage driving the CD stage has a large signal excursion and also contributes to distortion. So although it might be a solution, and it would be nice to investigate if this is still feasible, and it is one of the options to make this amplifier, I would say maybe there's another solution. Maybe we can do something else. So this is a discussion doing a CD stage, yes or no. We could also replace one CS stage with a 4-terminal stage. Well, the most promising solution would then be do it at the input, make the CS stage, the input CS stage, a differential pair, an anti-series connected CS stage. And we already know what to do. We know that we can achieve exactly the same noise performance, because the only thing we need to do is make the transistor twice as large and operate each transistor of the differential pair at a double current. And that would give the same noise performance and the same input capacitance. It would make the stage behave as the CS stage. So the cost is, of course, current and area. We didn't do this because we'd like you to do this. We'd like you to take this as a homework and to make the signal path of the two-stage amplifier with a differential pair input. So I already told you how to do and what we can expect. So I think it's quite doable. It will be 25% of your homework grade. Then the option, we can simply say, well, put another inverting stage in the loop. Basically, we don't know. We have no other reason for putting a stage in the loop than that we need inversion. And we didn't have it with 2 CS stages. And that is why option use the 4-terminal stage sounds like the most, let's say, logical one at this stage of the design. But we can also put a unity gain inverting feedback current amplifier in the loop, and that is a current mirror, and that is what we will do. So we are going to do a dual stage design, but we will add a unity gain inverting current amplifier. We simply invert the current of the first stage by passing it through a current mirror. And here is what you see. This is the slide diagram. So we know the width and the length and the drain and the current of the first transistor from the noise calculations. We have the dimensions of the P and the N transistor for the second one. So that is what you find there as well. It's and then we place a current mirror in between. But I first would like to see what we have. And so not immediately start with what does the current mirror contribute itself. Probably if you will put their transistors in there, you will also have FT, you have noise contribution, etc. Let's first think about putting an ideal inverting current amplifier, unity gain current amplifier in the loop. And that is just a current controlled current source with a gain of unity. That's why we make this step first. Then we know, let's say, don't do too much work at the point that we do not yet know what is the feasibility of this whole solution. Because everything you do, and it turns out to be, let's say, that the thing was not feasible, means that you did too much. And we don't like to do too much. Yes, we just be as lazy as possible. I think that's the best rule for designing. So don't do more in your design that you need at this stage. And we do it step by step so we keep control. So here you see the amplifier now for slide cap. It's good enough. It has the models for the transistors in it, in the geometry numbers, the current, and the current controlled current source. So then we know from the first course that we can design the bandwidth. The bandwidth simply follows from the product of the loop gain and the poles. So we need to evaluate the loop gain and the poles, and we can then calculate the bandwidth. You don't need slide cap to do so. You have all the values you have from your first simulations. You have the CISS, you have the GM of the stages, so you could simply make yourself a small signal model and with the hand calculations calculate the poles and the zeros. Maybe this is something we will do at a later stage to show you that it exactly matches, but of course we can also use slide cap for this purpose. Remember, very important, the loop gain is only meaningful, it only is the parameter that describes the deviation of the actual performance, the actual gain from the ideal gain, if the loop gain reference is selected properly. That means if the loop gain reference, which is a controlled source, gets a gain of infinity, the whole controller should act like a nuller. So basically, if we replace the loop gain reference with a nuller, the controller should become a nuller. That is not always the case. It will be the case if we select F1. If the gain of F1 gets infinity, it means it doesn't need any input current to produce any output current, which means that the input voltage and current of the first transistor can be both zero. So that could be a good choice. And we can check it. The asymptotic gain model really shows us if the asymptotic gain is equal to the ideal gain, and if not, then it is probably due to the fact that the loop gain reference could not be selected in such a way. For example, if you choose GM of the first transistor or of the second transistor, which is considered as one transistor in slide cap, just having two devices in parallel. But if you choose GM as reference variable, then in the transistor is local feedback from the drain to the gate, which means even if the gain of your transistor becomes infinite, the thing will never become a nuller because there's local feedback in the thing. The parameter C will be fixed by the drain gate capacitance. And we will show this in a later version. So we are going to design the bandwidth with the asymptotic gain model, and I just want to show you the result with slide cap, how to do this. And then, of course, F1 can later be implemented as a current mirror, and realize that the transistors then should have a low transconductance because of noise, because their current noise should be low, because their current noise is in parallel. The current noise of the mirror is in parallel with the current noise of the first transistor, which means that it just adds, and you need a, let's say, low GM stage to have less noise of this current mirror. But if we make a low noise current mirror and the cutoff frequency becomes low, then this whole circuit introduces another dominant pole in the loop, and that might also be a problem. So that will be interesting things to investigate later on if we are going to implement this with transistors. And this is, of course, a reason maybe not to do it this way and to do it like what we gave you as a homework, to use a differential pair, because then we don't have this extra stage and we can still make the inversion in the loop.